So today we are going to be talking about the process of software verification and validation, and what these terms really mean over and above what you would normally do in the course of the software testing process is that we are trying to make sure in a way that the software does exactly what it is meant to do. And we'll look at the difference between what validation is and what verification is specifically, and how this process differs from the process of software testing. We'll also take a look at what is called the clean room software development process, and this is a process whose philosophy is rooted in trying to ensure that the software can be gotten right in the first go, as opposed to having iterations where the software is released, bugs are found, it comes back and the bugs are fixed and so on. So it is what are the techniques that we can use to get software right in the first go so that it doesn't have to be rebuilt, and that's what we're going to conclude with in today's lecture. So the first question is, what is really the difference between verification and validation, and why do we want to take these two terms separately? Verification essentially deals with the question, are we building the product right, in the sense that there is a certain specification, a requirement specification that has been laid out, a requirements document that has been laid out. The document is then converted to a specification for the system, and as long as that conversion is accurate, you want to go back at the end of the cycle and check whether you met the specification of the software. And obviously, if you are using automated techniques to generate the code from the specification, then it will obviously match. But in the case that you don't and humans are involved in this process, we have to go back and make sure that we actually met the specifications that we started out with in the first place. Now, validation is really the question of, are we building the right product? That is, does it really help the user do what they want to do? So for example, if you have a document editor of some kind, let's say it's a word processor, and you don't have a spell check built into this at all. So this may be an issue with missed out requirements, and so these are the kind of questions that you will try to answer with the validation process. So you will go back to usage scenarios in the first place and see whether whatever you ended up building at the end of the day really meets the usage scenarios that were laid out to begin with. So this is also a process that has to be applied across the life cycle. So we can't just do verification, validation at the end of the life cycle and hope that everything is going to have come out right at that point in time, because what if it didn't is the question. The cost of fixing something, let's say that you missed out a requirement, let's say that you did not conform to the specification because you misunderstood it in some way, then the cost of finding that out in the end of the cycle is very, very high, and the cost of fixing it. And the earlier you catch that problem and fix it, the cheaper it is going to be for the software development process. So it's a whole life cycle process. In other words, it can't just be done towards the end, it has to be applied towards every stage within the process. And the principal objectives of verification validation, much like testing, for example, is the discovery of defects in the system is the first one. That is, we find out all the bugs in the system, and may not all be bugs that we want to fix, right? And that's the second question this tries to answer, is you assess whether these are the bugs that affect, for example, the usability of the system, that affect the usage scenarios that the software is most likely to be used for. So if you had a feature in there, for example, that was only going to be used for, say, 5% of the time, it's some kind of a complex configuration feature, it's going to be only used for 5% of the time, then even if there are one or two bugs pertaining to that feature, it may be okay to release the software at that point in time, and that's a call we'll have to make, and this process helps us make that call. So what are the goals of verification and validation? The goals are that they establish, the basic goal is that it establishes confidence that the software is fit for the purpose for which it is being built. So going back to the first slide that we saw on this, what it's trying to do is to ensure that we're building the product right, is meeting the specifications or meeting the requirements that were laid out by the user. Also, it's going to try to ensure that this is the right product for the user in the first place. So the software is fit for the purpose, right? It obviously does not mean that the software is completely defect free. what it means is that this can actually accomplish the task it set out to do. It must be good enough for the intended usage of the product, and it will determine the degree of confidence that is needed as far as this particular software goes. So, depending on the system's purpose, in this case, user expectations, marketing environment, etc., what are the factors that influence the confidence level of a particular piece of software? It's worth looking at that, because those are the factors that we have to end up attacking within the verification and validation process. So, the first factor is that of the software function. What is it that the software itself does, right? So, how critical is the software to the organization? So, what is the software function within the entire organization that this is meant to serve? What is the expectation of the user is the second thing that would have to be considered, right? The user may have very low expectations of certain kinds of software, or they may have very high expectations of the degree of automation that a piece of software is going to bring to them, right? So, for example, if you're going to put out a word processor kind of software, it's not going to write documents on its own. Right? It's unreasonable to expect something like that to happen. Whereas in enterprise automation software, so this is not desktop software, in enterprise automation software, the kind of ERP systems, for example, that exist within the enterprise, the expectation is that it will largely automate the business process of the enterprise, and it will take the human touch away from most of this process, and it becomes much more efficient as a result. Then there may be market conditions. So, market conditions may drive the fact that the software product has to go to market early. By early, we mean that it may be at a point in time. If you're aiming for a zero defect kind of software, you may not be there yet. But market conditions may be dictating that unless you release the software in a particular window of opportunity, then there is no point releasing the software at all, because the competitor has probably beaten you to the market with it, with pretty much exactly the same piece of software that somebody else is building. So, that window of opportunity, or the need for a software such as this may not exist outside the window. So, it's either driven by competition, or it is driven by the need for such a piece of software. It may become obsoleted because of the fact that some other environmental conditions change, and the software is no longer needed in the first place. So, getting to market early may be a concern, and this is also something that is going to end up driving the confidence building process. So, what is the level of confidence you need to have? What is the amount of risk that the organization is willing to undertake in order to release the software product into the market? So, there can be two kinds of, at the highest level, there is a dichotomy of verification methods, right. So, the static and dynamic verification is what we call them. Static verification is essentially something that is done with the code base and not with the actual product. So, for example, you may be using the code base, you may be using the documentation, you may be using the design diagrams, you may be using the specifications and so on, but you are not actually playing with the built product. So, you are not testing the product, in other words, in any kind of dynamic sense. Largely it has to do with software inspections, right. Software inspections can be supplemented by code analysis and so on, and all of this belong to a set of methods which are static in nature. So, code analysis through programs like LINT, for example, for C programs, and there may be equivalent programs for Java as well. So, software inspections, manual inspections of the code, the documents and so on. Then there is software testing. Testing is a dynamic verification process. So, in testing, you actually write some test cases, drive the software through the conditions that it will be expected to encounter, and depending on how the software behaves, you determine whether the software is functioning properly, it meets the specifications or not, and this is completely dynamic. So, it is actually executed, whereas in the static method, it is not executed. Purely some set of inspections or some either an automated inspection or a manual inspection is done to determine whether the software has been built right. So, program testing can typically reveal a presence of errors, right. It cannot reveal the absence of errors. So, how do you make sure that errors do not exist? Certainly, when you test a program, it can never be completely exhaustive, right. So, there can be hundreds of thousands of test cases for a program that can take in, say, 10 inputs, which can take in a variety of values. It is impossible to test every single set of values. So, the test reveals certain errors that may exist. So, for example, you may do a validation test, give it the wrong kind of input. So, it is a date, and the date is always expected in the day, the month, year format, and you feed it a date in a different format and see whether it throws up an exception. right. So that is one thing that you ought to test. But certainly the other thing that you ought to test is that a variety of correct formats that it accepts is also something that is going to go through. So is there an absence of errors under certain conditions is something that you have to test for as well. And program testing does not reveal the absence of an error, it only reveals the presence of an error. And non-functional, where non-functional requirements are concerned, the only validation technique is execution. It's dynamic in nature, because performance, for example, you can never predict. Although there are predictive or analytical techniques for predicting performance, largely something like reliability of performance has to be determined only by running the software under certain conditions. Now, how does it behave with 100 users in the system executing concurrently? Is it reliable if it ran for 30 days under this kind of load conditions, etc., etc. So, software or program testing, which is a dynamic technique, not something that we are going to go into here, because we have already seen dynamic techniques and how to do OO testing, etc. But it is obviously used in conjunction with the static methods, static verification techniques, to provide complete coverage or complete validation coverage. So testing can also be of multiple types. Defect testing are basically tests that are designed to discover system defects, as is indicated here. And a successful defect test is one which reveals the presence of defects in the system. So if a test was checking to see whether you are accepting only the correct format of the input, and the test actually showed that no, you are taking in some formats that are not the correct format as well. So there are two things that can be tested there, right. The first thing is that you give it a correct format and it actually accepts it and doesn't give out an error, is the first thing. The second thing is you give it a wrong format and ensure that it generates an error. So a successful defect test is one which actually reveals the presence of a defect or the presence of a bug in the software. And validation testing is basically intended to show that the software meet its requirements. Now, if there was no requirement, for example, to validate the format of the input, there is no point in having a test that checks the format of the input. Yet the system may kind of be unusable really if you didn't validate the format, because different people would be entering these dates in different formats. So here a successful test is one that shows that requirements have been properly implemented and that the system is usable. So that is something that needs to be added to validation testing, because in validation, are we building the right product is what we end up asking. And so here it's not just that it reveals the presence of a defect, but here it's a test that shows that it conforms to the requirements and that the requirements are complete in nature. Now, debugging and testing are also slightly different process. Again, very dynamic in nature. Here is you're putting the software through the paces and trying to determine whether it is meeting certain requirements. But in the what is the difference between debugging and testing? They are distinct processes. Testing is meant to indicate that there is a defect in the system, and debugging is a process of determining, localizing the defect. Where is the defect existent, and removing the defect is the process of debugging. So while verification validation is concerned primarily with establishing the existence of defects, debugging is concerned with removing the errors, locating and repairing these errors. So typically you end up forming a hypothesis. The way you go about debugging is, okay, the system, for example, is failing with this set of inputs. Let's say that you gave it a value greater than 10 for a particular integer value that it is expecting to take, and the system failed after some point in time. So you form a hypothesis saying, okay, here is how the value is processed, here's what's done with the value. You kind of know the flow of the program, the control flow of the program, and how the inputs are getting used in this control flow. And based on that, you form a hypothesis, and then you test these hypotheses to figure out whether there is a system error. So you might start localizing these within, there might be 4 modules in the system. You test the first module, for example, because you feel that the validation of the input is not being done right, and it is passing a piece of input that it should not be passing down to the rest of the program. If that is the case, you can just test that module by testing whether it's doing the validation. That's a hypothesis. The validation is not being done right. So you form a set of such hypotheses, and that's how debugging ends up getting done. So here is a diagrammatic view of the debugging process. So you have a set of test results to start with. Typically, you have to locate where the error is. The test results also typically indicate the software, not just where the software failed, not just that the software failed, but where did it fail. So typically the line number in a program is something that is indicated as part of the test result. You take that and then you take the specification along with that and figure out where you ended up deviating from the specification, right? What is the specification and why is the test failing this particular specification? So you then design error repair around that, you repair the error, and then you have to retest the program with the same set of test cases that caused it to fail in the first place. And an important fact here is that a set of test cases have been generated, the program failed the set of test cases, you fix the failure, and now it may not be just sufficient to rerun the original set of test cases in the first place. It may be, it may not be. You may need to add certain tests because you made certain changes to the structure of the program itself. Some of the tests may now become invalid because of the changes to the structure. So you have to be careful about that. But certainly the cases which caused the system to fail in the first place, it has to pass. And then if any new additional test cases are added, those are run as well before you're done with the debugging process, right? So having seen the difference between debugging and testing, so these are all the dynamic methods of verification and validation that we talked about. Remember, there were static methods which focused on inspection, either manual or automated inspection. Then there were dynamic methods which focused on testing. So we kind of looked at the different methods of testing, the difference between the testing and debugging process at a high level. And the question is, what else should be done? What is the overall process of verification and validation? What is the kind of planning that goes into making this process happen? So the first thing is, obviously planning is required in order to get the most out of the testing and inspection process. So since you are also doing manual inspections of the code base of designs, you're discussing the design documents before you move on, there is some degree of optimality that can be achieved by focusing your attention on specific pieces of the system. Say there is a very critical part of the system, maybe you only want to do formal specifications and go down that route. Maybe there is a piece of the system that has been thoroughly inspected and you have a high degree of confidence in that part of the system. Maybe the testing does not have to be that exhaustive in that particular module of the system, and so on. So the planning is something that has to be done and should start very, very early in the development process. In fact, the V&V development process, the verification validation development process, emphasizes that you start writing test cases as soon as the requirements are written, or as soon as the specification is written. You don't wait, and so the testing process happens in parallel with the development process, and we shall take a look at the process itself in a little while. And so certainly there should be a balance between the static verification methods and the testing methods, the dynamic verification methods, and just like we talked about a little while ago. And finally, test planning is all about defining standards for the testing process. So for example, what is the test environment going to be like? What degree of scalability testing are you going to end up doing? If this system is going to take 100,000 users at any given point in time, you're not going to be able to test it for 100,000 users. So you have to have some means of building up confidence that when tested for 100 users, you can somehow extrapolate those results to ensure that the system is going to work with the same level of performance with 100,000 users. Is this system going to scale, is the question that is going to be asked. And so in test planning, you try to build confidence that the tests that you're doing are indeed going to let you know whether the system is going to scale or not. So here is again a diagram of what is the verification model of development. You start off with the requirement specification. In this case, with the requirement specification, you can start writing the acceptance test plan, because the requirement specification is done by the customer, and the customer is ultimately the one who is going to accept the system. So the requirement specification will lead to the acceptance test plan, which in turn will lead to actually doing the acceptance tests when the software is ready to be acceptance tested. Then the system specification is written. The system specification can also go towards the acceptance test plan, because in some cases the user may be involved in the system specification, but more often than not, we'll take the right side arrow of this particular box coming down into a system integration test plan, because once you specify the system, Let's say here are the 4 different modules, here's the specification of each one of the modules of the system. So that's what a functional specification looks like. In that case, you have to have some kind of an integration test plan that is built around the specification and design, right? And then the detailed design, the system design and the specification together go into creating the system integration test plan, because the design is also responsible for modularizing the software. It is responsible for bringing it up to say we're going to use these components, we're going to build these modules, and the modules themselves or the components themselves may be individual units of work that are put together by different people. So even though they may be tested individually, there has to be some test that covers the cohesiveness of these different modules. Once they come together, is it really fulfilling the specifications, even though they work very well at a unit level. So that's what system design and specifications end up driving, the integration test plan. And finally, the detailed design may drive the detailed design typically ends up driving the unit test plan, which is the last box on this side of the diagram, but it may also contribute to some subsystem integration test plan. So if you hierarchically break down the system into subsystems of lower and lower complexity, then there may be some subsystem integration. But at a high level, you may not end up seeing this subsystem integration test plan box. What you'll see is an acceptance test plan box, a system integration test plan, and finally the unit test plan pieces of it. And so detailed design will drive the unit test plan, and as soon as the code is done, the unit tests are run on the code for each module. This is done on an individual module level, and once the code has been unit tested or the components have been unit tested, then subsystem integration and system integration testing is done, and using the appropriate plans. Either there is a subsystem integration test plan or a system integration test plan. And once this is done, it then goes into acceptance testing using acceptance test plans that you have already created before. So it's kind of like a V process, if you will. It starts from this requirement specification and goes back to the product or the service that is being delivered to the customer, and what are the different stages of testing as it is integrated with the development process itself, is what this tries to show you. So this is also something that you might have seen during the software testing part of it, but here's the structure of a software test plan. The software test plan primarily focuses on what is the testing process going to be, right? So how are we going to test the software? It also focuses on things like what is the test environment going to look like. Are you going to have a full scale test environment which exactly duplicates what the production environment is going to be like? Are you going to have a scaled down version of this? If there is a scaled down version, is there a process to extrapolating the results to get at what the software is going to behave like in the fully scaled up version or the production under production conditions? Then it is typically going to have to test every single requirement. So there needs to be some kind of requirement traceability that says here is a test that tests requirement 1.2, here is a test that tests requirement 1.3, and so on, because at the end of the day you have to have confidence that every user requirement has been tested and works, right? So what are the different items that are being tested? What is the testing schedule is one thing that it puts together. So if there are 450 tests that need to be done because there are 450 requirements, and each test kind of breaks down into 10 other subtests, then what is the schedule? All this is going to take time, it's going to take resources. What is the plan going to look like? What are the recording procedures? Not just sufficient to do the test, but you have to record the results of the test in a very systematic fashion so that you can go back and analyze the results at a later point in time. So what is the recording procedure going to look like? What exactly, in fact, the template of the test results going to look like is very important to specify upfront. And then what are the hardware and software requirements for testing? Do I need just one server? I'm going to simulate the system, or I need a bank of servers because I'm going to run the real system on here. And so is there a test harness that is required, a software test harness, etc.? Are there any constraints on the testing? No, I cannot test this particular requirement because it is testing, let's say, the degree of user friendliness. It's a very subjective kind of a requirement, and maybe it's something that cannot be tested objectively. So the testing process, so we just went through this. Software inspections, coming down to this, so we've kind of seen testing. Remember, we broke up the entire verification validation into static and dynamic process. Static process dealt with inspections, dynamic process dealt with testing, and we've gone over the dynamic process. Coming back to the static process, inspection, either manual or automated, is a very key feature of how this is done. So software inspections essentially involve people examining the source representation. By source representation, we mean code, it can mean design documents, it can mean a specification which is used to generate the code, etc., etc. It can mean an architecture document, etc. And the main goal of this is to try and improve the design, improve the code, improve the architecture, improve the way specifications are done, and so on. So the aim is to discover anomalies or defects within this source representation. So it's typically done before implementation so that you can catch things up front, and the earlier you do it within the process, the more beneficial this is likely to prove, because a bug or a software defect or an error that is caught up early in the cycle is going to be much cheaper to fix, as we've already seen. It can be applied to any representation like we've already seen before, and it has been shown to be a pretty effective technique for discovering program errors. It not necessarily mean coding errors. There could be a fundamental design flaw in the system, for example, that shows that a security breach is occurring in the system. Right? A design flaw could be that you're not doing any kind of encryption between two different processes within the design. This could essentially result in a potential security breach in one process translating to a security breach in the second process, because there is no encryption going on between these two, or the data flowing from one process to another is subject to snooping by a third party who can potentially corrupt the data, attack the system, and so on. So there can be a design flaw, or there can be a coding flaw in the system. So for example, somebody can spot the fact that a loop is never going to terminate because one of the conditions that they can think of which can occur in the program is going to cause it to loop forever. So there can be different kinds of flaws, as we shall take a look at shortly. Again, this can be an incremental process. It can be a process that takes place several times, because you could end up finding defects, say in the first part of the design that you are discussing, or the code that you are discussing. You stop the inspection at that point, you go back, fix these, come back and continue the inspection, or typically what may happen, and this is true even with testing, one defect can mask several other defects. So in tests, when the first defect is found, the test stop at that point in time so that you can go back and fix these errors. Just like several executions of a test run may be required, several inspections can be required to actually catch all the defects. The second point that is important here is the reuse domain in the programming knowledge, right, that exists. Reviewers are likely to have seen the types of errors that are commonly committed. Right. So for example, one of the things that are commonly done in coding is that variable is not initialized before it is used, and so this is something that people know to watch out for when they are doing an inspection, as a result of which they are likely to catch it pretty quickly. The other thing may be coding standards that are set up by the organization. Typically a coding standard may say there is a certain naming nomenclature that has to be used, a nomenclature that has to be used throughout the program. So for example, module methods are named by intercap notations, could be a particular coding standard, and a violation of that can be easily be caught by people because they've been doing this for a long time and they know exactly what to look for in this particular case. So once again, inspections and testing are complementary process. So they're not something that are mutually exclusive. Both of them have to be done. Inspections are typically applied at a higher level of design. It can be applied to code. In fact, in some cases it is, but it is not trying to catch code errors such as the infinite loop of a program, etc. Typically, it is meant to catch design errors of a higher level. Just like the security design error that we just saw a little while ago, and both of them obviously have to be used during the entire process. So inspections are something that can check conformance with the specification. Actually, the third bullet is not completely true, in the sense that inspections, if anything, can can understand the true intent of the customer when they specified the requirements, because there are humans involved who are sometimes doing these inspections. Whereas testing is typically automated, it's an automated process and you've written the test, and it's hard to sometimes understand it. So there you're going exactly as per specifications and you may not be able to understand the true intent of the customer in specifying the requirements. So in that case, again, inspections can check conformance with the specification. Also it can go beyond that. It can be used in a situation wherein there's a human on the team, there's an architect, there's a business analyst or a systems analyst who understands what the customer meant when they wrote down a particular requirement. In that case, they can bring that knowledge to bear on the inspection process and make that be that much more useful. The disadvantages of inspections obviously are it cannot test non-functional requirements. So it cannot test user friendliness, it cannot test performance, it cannot test reliability, and so on, because they are not actually playing with the software at that point in time. They are not executing the software, they are not executing the code in order to test for a particular property. Whereas in testing you can catch that. There can be tests for non-functional requirements as well. A test, for example, that will measure the end-to-end response time of a particular request, and if it exceeds the threshold, you know that you have broken a non-functional requirement very clearly, but that can't be done during the inspection process. However, there can be hints that a particular piece of program code or a particular design is going to be too resource intensive. In other words, say you can make out that a algorithm that is going to be used in encryption is far too CPU intensive. So given the fact that there could be hundreds of users banging on the system simultaneously, that's not the right algorithm to be used. That kind of decision making can be done with the inspection process much earlier on in the life cycle. So program inspections are basically formalized approach. They are intended to explicitly check for defect detection, and certainly it is not going to help correct it, although suggestions may come out during the inspection process as to how to correct a particular defect. Typically we are looking for high level logical errors, we are looking for design flaws, we are looking for architectural suggestions and so on. The choice of a particular component, the choice of a particular data structure in a certain situation, but we are not looking for very small code anomalies such as this is an uninitialized variable and so on. There can be automated tools which do some of those things, as we shall see in the next part of the talk. So continuing on, what are some of the preconditions for an inspection to take place? We will take a look at the preconditions, then we should take a look at the inspection process, what are the kinds of errors that you are going to likely look for in an inspection and so on. So the preconditions are that a precise specification is available, because you are always going to refer back to what is it that this module is supposed to be doing, what is it that the software is supposed to be doing, what is it that this function is supposed to be doing, and so on. So the precise specification must be available. So whatever standards that is it that you are checking against, so suppose you are checking against a coding standard, suppose you are checking against a design standard, whether the user design patterns is appropriately being met. Now those guidelines must be published appropriately, must be published in advance, must be pretty clear, and all the team members involved in the inspection must be familiar with these guidelines. Also, syntactically correct representations of the source must be available. There is no point in going through a document which is full of spelling mistakes, for example. There is no point in going through code which is not going to compile. Since a compiler can automatically check this using a machine, there is no point in a human sitting down and trying to figure out whether this code is going to compile or not. That is not what an inspection is meant to do at all. Inspection is meant to catch logical errors in the program. So it should basically pass a compile test, should have passed the compile test already. The error checklist must be available well in advance. What are the kind of errors we are looking for? So that checklist should be, that categorization should exist, and we shall take a look at an example categorization. And obviously there has to be management buy-off on the whole process. Because this is going to increase costs. No question about it, because there is a team of designers who are sitting there and not actually designing, but they are reviewing the design of somebody else. So this is going to cost them, but the cost that is borne early on in the process is likely to save a lot more cost down the line, and that is a fairly proven fact through empirical evidence. So it is something that needs buy-in from the management. The last thing, which is probably the most important, is that this should not be used by management as a blame pointing exercise. So in other words, this can't be used to point fingers at a programmer or a designer and say, see, you're doing such a terrible job, you're going to be fired the next year or whatever. It's not meant for that. It's meant to fix the software. It's not meant to figure out. It's not an appraisal tool, in other words. And we have to be very, very careful about this, because often this is what ends up happening within software development. So what does the procedure itself look like? So the procedure is fairly straightforward. The system overview is first presented to the inspection team. So somebody presents, not the developer, somebody else, and we shall take a look at the roles in the next slide. But so somebody presents the module that is being reviewed. What is the overall goal of the module? What is the specification of the module like? So what is the module design look like that is now being reviewed, and so on. And then all the documents should have been presented well in advance. Actually, this is not something that takes place after the system overview, or the code and associated documents should be distributed to the team well in advance, so that they could have studied this and come forward with opinions already. Then the process of inspection itself takes place. So there is a meeting in which all these people get together. The design is presented formally by a reader and then reviewed by all the team members. Modifications are made to repair all the discovered errors, and re-inspection may be done at that point. So what are the roles of the people involved in the inspection process? So the author is the first role, pretty clear. This is the person who produced the source, produced the design, produced the code, whatever. The inspector is a designated role which says that this is a person responsible for determining defects, or determining whether this design passes the standards that they have set for the organization. A reader is like a third party who presents this to the inspection team, who presents the design, who presents the code, etc. to the inspection team. It could be the same person as the author. It's typically, these are roles, remember, not the people. And scribe minutes the meeting. A moderator essentially makes sure that this is an impartial evaluation process, and somebody is not out there to get the author. And process improvement person, usually from quality assurance, is sitting there to try and figure out whether the process of inspection itself, the process of development, the process of verification, the process of inspection can be improved, can be made more efficient, can be made less costly, and so on. So this is typically the roles. So what are the checklists of errors that one must have, that one is checking for? We're going to go through, instead of examples, let's actually go through the different categories of inspection checklists that we can have. The first category is what are called data faults. Data faults are typically those that can be checked by a compiler, right? So this may not be something that is done through manual inspection. Remember, these categories can be applied both to the manual inspection process as well as to an automated static verification process. So data faults are the variables initialized. If it is not, it could likely result in some arbitrary error later. Have all the constants been properly named? Are you using hard-coded values, or are you using a constant? Now this is a stylistic feature, a code style feature. Instead of using hard-coded values, one must always use a named constant, right? So that is something that the compiler is not going to catch. It has to be caught by an inspection team. Are the array bounds being met appropriately? For example, some programming languages always start array numbering from 1, other programming languages like C started from 0. So is the array bound array size minus 1 or array size itself, right? So are delimiters existent for all the character strings that are being used in the program? Because if it is printed or if it is passed to another program, it may not print it appropriately. This is something that testing might be able to catch. Testing may not be able to catch something like this as well. So this is important for manual inspection. So these are the kinds of data faults that one can look for. Some of these, such as variables being used before they are declared, a variable not being initialized, etc., can be caught through a compiler or a static analyzer. The rest of them typically have to be done manually. Control faults is another category of faults that you can look for. Control faults are things like, for each conditional, is the condition correct? Right? Is each loop certain to terminate? Is there a possibility of an infinite loop under different conditions that this loop can be entered into? So in switch statements, are all possible cases accounted for? Is there a default case for a switch statement that is provided? Again, something that can possibly be checked by a compiler. A more intelligent compiler can check for some of these things. Third category is interface faults. In interface faults, you primarily check some simple things such as the number of parameters, the formal types of the parameters matching the normal types of parameters, and so on. right? If there is shared memory access, which is part of the interface, then do all the components have the same shared memory structure? Do they have the same view of that chunk of shared memory? If not, then they could be talking at cross purposes with each other. Storage management faults are typically have to do with managing memory, which is a fairly scarce resource in most programs. So if a link structure is modified, for example, have you appropriately released the memory? If you are using dynamic storage for something like this, are you releasing the memory? In a case of the linked list, are you patching up the pointers appropriately so that the linked list is still now unbroken, right? So that's the kind of storage management faults that you can look for. Exception management: if a function declares 3 or 4 exceptions as part of its specification, then when you call that function, are you making sure that you handle every one of those exceptions that can arise from that, is the question that you have to ask yourself. So are all exceptions being accounted for? So the next one is coding standards. Are you using the appropriate nomenclature? Are you using intercap naming for the functions, small letter naming for the variables, and so on, whatever standard that happens to be within that organization. And at the design level, are you using the patterns that are mandated that you use within the design? So for example, the observer pattern, is it being used? The singleton pattern, is the factory method being used to create new instances that have to be created, and so on. Then there can be efficiency standards that you're looking for. Are you making efficient use of memory? Are you making efficient use of the CPU? Is there a better algorithm that can be used which uses a lower amount of CPU, for example? Are you using scarce resources such as network bandwidth, IO bandwidth, memory, CPU, etc. appropriately? Are there better methods of doing this? Is something that can also be checked for and be part of an inspection checklist. So the inspection rate, I mean, this is purely meant to show these are recommended values: 500 statements an hour during overview, 125 source statements an hour during individual preparation, and 90 to 125 statements during the actual inspection process. What this is meant to show is that this is a fairly expensive process. A program can consist of thousands of lines of code. Obviously, you cannot inspect every single line of code, right? Because it's very expensive to sit there and inspect every line of code, just as formal methods cannot be applied to a large program in its entirety. So you have to pick the critical portions of the program, the mission critical portions, which can cause a lot of modules to fail if this one module were not right, and then go ahead with inspection for just those critical modules. It's an expensive process, and therefore the buy-in of management is very, very important. So moving ahead to static analysis, static analyzers are basically programs such as LINT, right? They're software tools that can do source code checking. It can check source text. In the case of designs, for example, it can check whether a UML diagram is complete. Are there, for example, the relationship values may not be okay. Is it one to one versus one to many, and so on. So they basically parse the program text. They build up an abstract syntax notation just as a compiler would do, and then you apply certain rules that has been set up by the user to do some checking against. So we'll take a look at some of these examples. They are very effective as an aid to inspections. So they don't replace inspections completely. There are certain things that cannot be checked with static program verifiers or program checkers. So stylistic guidelines, for example, is something that they cannot check. The people have to be involved in this process. So static analysis checks, very similar. The data faults, they can check using before initialization. Very easy check to perform automatically, right? So a variable is used before it has been initialized. A variable is declared but never used in the program. So this can be pointed out by a compiler, a static program checker, to say you're using this variable, why don't you just get rid of, you're declaring this variable but not using it anywhere. So why don't you get rid of it? You're just occupying memory, right? It's assigned twice, so x equal to 3 and x equal to 4. So the first assignment is effectively useless. Before it is used anywhere, if another assignment is being made, the first assignment can be completely bypassed, right? So that's a check that can be done. Array bound violations also, in some cases this can be done statically. In some cases you can't do this, because if it is completely dynamic in nature, then static program checkers is not going to help. Similarly, we have control faults, interface faults, etc. The same category of faults that we saw in the inspection checklist can to some extent be automated. Whatever can be automated through the use of a software tool falls under the static analysis checks. So, simple things like in an interface fault, the number of parameters is there's a mismatch. So, this function foo has been specified as taking in 4 input parameters, and when you're calling it, you're only giving 3, and there's no default value for the 4th one that foo accepts. There's an obvious error. The type, there can be a type mismatch also, right? So, for foo is expecting an integer value for the first parameter, but what you're passing it is a floating point value, which cannot be cast down to an integer value. Type mismatches can easily be caught as well. So, just like you have unused variables, you can have unused functions. So, you're declaring a function, you have implemented the functions, never called anywhere within your program. Do you really want to keep this function or move it to be part of some library which makes more efficient use of the space? So, the stages of static analysis are that can be control flow analysis, data use analysis, and interface analysis, and corresponding to the kinds of faults that it is checking for, all of these can be used. So, there can also be more complex static analyzers. There can be complex tools that do things like path analysis. What is the complexity of the program? What is the path of the longest number of hops that the program might end up taking? Things like this. So, it can look at the entire programs as opposed to individual modules and simple rules. Very useful potentially, depending on how efficiently it can do this. Information flow analysis identifies the dependencies of output variables. So, for example, an output variable is coming back from a function that you have called, but you really never use that return value at all. So, that's an example here as well. Here is an example. We are not going to go into a great deal of detail about a tool called LINT. Right, you all heard of a tool called LINT. It does static analysis on C programs, and it can point out some simple things like a variable is used before being initialized. It can point out that a variable has been declared but never used, and so on. But this is something that you can try out for yourself. Write a small program, run C programs. LINT is meant for C, but there are LINT available for other languages as well. It's very programming language dependent. And then run LINT on it and see the kinds of error messages that it ends up giving you, right. So, the next step that we will go into as far as the verification validation process is concerned is formal methods. Something that we have seen before as part of this course is how do we do formal methods, how the use of abstract data types and so on. This is the ultimate static verification technique, because if you are using, if you are formally specifying the software and then code generating it, because it's executable specifications, remember the term executable specifications, then you can always verify that the code that is being generated is meeting the specifications in some way. So, the specifications are formal, then a mathematical model can be built of the code and a mathematical model of the specification as well, and see whether these two things match. So, the arguments for formal methods is something that we have seen earlier already. It produces a specification. The thing is that it can really catch errors very early on. In fact, it avoids the use of errors completely, because specifications can be run through verifiers that basically check the completeness of a specification, that checks for consistency checks and so on. So, even before implementation is done, you can do some analysis on this program. It's obviously very useful. It's also very expensive. Even small and the tools that exist are not very prone to usage by regular programmers. It requires specialized knowledge and training in these tools and languages. Very expensive, and it might be possible to reach a level of confidence in verification and validation without the use of formal methods as well, in a much cheaper way through inspections and static analysis techniques and so on. So, one has to be very careful about how you end up using this. So, there can be formal methods, which is an extreme end of the scale type of process. There can be static analysis, which is kind of a middle of the road process, which is automated, so you don't have to depend on the vagaries of human nature. Then there can be inspection processes which do depend on humans, which depend on the expertise of humans, but the added advantage there is that you can get the experience that these people have been through from doing this many times before, and therefore they may be able to catch things that a program may not be able to catch. So that's the scale. That's what the scale looks like. At one end is the formal methods, very accurate, can really save cost because it can catch defects very early on, but very expensive. And the other end of the scale is inspections, which is done by humans and which can catch certain types of errors, and in between is the static analysis part of it. So the key points, we won't go into clean room development at this point in time. In the next lecture, we will take a look at a process called clean room software development, which takes whose philosophy mainly is that if it can be done right for the first time, then that's the way we should go. We should not try to develop software fast with some errors and then come back and fix it. Rather, we should take the additional amount of time in order to do it appropriately. And the word clean room is borrowed from the chip development or the chip processing, chip manufacturing process, in which clean room development is done. So you start from scratch always, and you don't incorporate things from outside and so on. We'll go into the details of the process in the next lecture. So this is it about verification, validation. Very important process that has to be appropriately put into the various phases of the software development lifecycle. It can't all be done in the end, can't all be done at the beginning. So it's something that has appropriate steps during the development lifecycle itself, and care has to be taken to see that this is part of the planning for the software project.